High Voltage takes center stage in this brand new season of Hitachi Energy's Power Pulse podcast. We promise to bring you great content from the brightest minds in the business. We'll discuss challenges, opportunities, and all the hot topics any high voltage enthusiast, or anyone interested in sustainability for that matter, is sure to enjoy. In this episode of the podcast, we invited Markus Bujotzek to come along and tell us how high voltage products are researched and developed. Markus is the Global Technology Manager for Circuit Breakers at Hitachi Energy. He holds a couple of impressive degrees, namely a Master's in Electrical Engineering from the University of Aachen and a PhD in High Voltage Engineering from ETH Zurich. Have you ever heard of the full electrical guy? Markus is that guy. If you haven't, there's one easy way to fix it. Stay tuned.
Welcome back to our series on high voltage with Hitachi Energy. I'm your host, Sam Dash, and today I'm speaking with Markus Bujotzek. Hi, Markus. Thanks for joining me.
Hi, Sam.
So, Markus, I've been told that you are the typical full electrical guy, which is quite a phrase. I love that as a title. I wish that was my title. You studied electrical engineering at Aachen, is that right?
Yes, it's in Germany.
And did your PhD in high voltage at ETH, which is the technical university. Is this the most common path to work in research and development?
Yes. And no, I mean, it's very typical for us to be engineers, electrical engineers or mechanical engineers, but also physicists. What is maybe not the most common is cities, right? I mean, Aachen is quite popular. Also, ETH Zurich are popular, but we are very international. So we have people all around the places. So the engineering part, yes, the locations are not most common, but popular, I would say.
And so do people call you full electrical guy in the hallway?
No. Maybe my boss. Yeah. Because he's a mechanical engineer and, there's some competition sometimes between the mechanical engineers and the electrical one already at universities. So sometimes we tease each other a bit, right? Yeah. But there is also a lot of physicists, material scientists. Right. So it's very multidisciplinary, I would say. Mm-hmm. But of course, engineering, we are an engineering company somehow, I feel at least.
Right. Yes, you're well placed. If I were to come to you with some brilliant idea for a new switchgear, which, would be quite a leap since I don't have the background that you do. Yeah. But if I were to come to you, what process would this idea undergo on your end of things?
If you would come up with a great, revolutionary idea to us, if it would be internally, we have a process to create project proposals and then develop technology. It could be, of course, also from outside, from university or somewhere else. Then we would draft a project proposal and start a project, an R&D project. Typically, that takes quite some time. So you have first some fundamental research, typically, or technology development, and later product development.
And when you say quite some time, what's the sort of range? Like on the lower end, it would take a year, and on the higher end, it would take 5 years, or is that very, very off?
Yeah, it's not that off. But for technology development, so if you want to move from one technology to another, as we are doing now in switchgear a lot, moving from one insulating gas to another one, that can take decades, right? So I started in research like 18 years ago, and there we were already running research on alternatives to the currently used gas, SF6, this insulation gas. And then after you have kind of reached a certain maturity of technology development is kind of somehow over, you move to product development, then it takes a couple of years to develop a product. 2-3 years at least until you have it fully out, right?
Right. So we're not talking about anything happening overnight.
No.
Yeah.
Not at all.
And so once the product is deemed viable, what is the criteria that this product must follow?
That's difficult to answer. I mean, there's a lot of things the product must follow. But of course, I mean, there are some core pillars like sustainability, safety, but also the pure performance, technical performance it must follow, right? So you need to fulfill certain ratings. So the switchgear, it's very standardized in a way. So there are international standards and there is ratings, and you want to fulfill a certain voltage level or current level, then you need to show certain test duties. This you need to test in development and later in certification. So you obtain like a degree, right? At the end, you go to an independent lab and get the certificate. Yes, I'm allowed to call my product, 420,000 volts breaker for 60,000 amps or whatever, right?
Right.
So that's quite a long process for that.
Yeah, of course. How long does this process take at minimum, and what's the sort of longest this process has taken, accounting for various obstacles along the way?
I mean, it always depends if you just do an upgrade and say, I want to move my limit from one value to another. So I want to make the switchgear or the breaker interrupting instead of 50,000 amps, it should interrupt 60,000 amps. Or if you develop a full new, world first eco-based product, right? So these upgrades, they take, I would say, at least also like 2 years, right? And when you include the technology development for a new technology like the Iconic, that can take decades, right? Because it's not only to develop a prototype, you need to implement it in the factories, you need to have the whole supply chain, you need to test it. Or just the pure type testing phase can take half a year, for instance, right?
And then how many people are involved in that process over that whole time period from start to finish? And then how on earth do you sort of find those people and maintain that workforce? I can imagine there's a lot of specific training involved.
Yeah, so if you take all the people involved, it's a lot, right? Because as I said, there is not like a one-man show there, right? It's always a team. And so the core R&D team, you could say for such a project to develop new product, maybe 20 people in the core, but there is easily 100 people involved. If you take the laboratories, you take supply chain, you take the factories, all around that, the research before and support from research to answer questions in case you run into obstacles and so on. People developing simulation tools because we use a lot of simulation method to do that. So first that needs to be established. But the core team, which then really works for a couple of years on the product development, I would say that's typically like 20 people involved.
Is it quite a specialized area of knowledge and expertise that you look for those 20 or so people? And is it hard to keep them invested and make sure that they're up to date on all the newest innovation? I
mean, I would say the difficulty is to find the right mix of people, right? Because you need like different disciplines. So you need mechanical engineers, flow specialists, electric field specialists, whatsoever, right? Different material people. But then you need them to also collaborate in a way that some people are more the practical ones to do the experiments, to analyze the data. Others are more on the design side, the creative ones. And so you need a nice diversity somehow. Then the story works pretty well. And we have also technical career paths where you have people which are really senior and senior principal engineers, which are there with a knowledge of 20 years plus. Those are mixed then with guys which come fresh from university or after a PhD or from research center, because we have a bit the split also between research and development. So this research part is rather done in research, and the development then later on is done on the development side, on technology centers. And if you mix those people well, then it's like self-maintaining a bit, because the experienced ones can educate the less experienced one. Those bring the new ideas from the universities. Certain physics do not change too much, but certain methods change a lot, like design for manufacturing or simulation method, numerics, the computers getting better, and 3D simulations instead of 2D and this kind of stuff, right?
Is it generally your responsibility to do that curatorial work of creating that ideal recipe?
I don't know exactly what you mean with
sort of that varied collection of experts and people on that workforce. Do you yourself sort of curate?
Me personally, you mean? I know we are organized in a way we have technology centers. So I had that job before. So I'm 18 years in a company, and I was running a department within here, Swiss Technology Center, where we have all the people. Now I'm kind of, as a global technology manager, I'm the customer to this technology center. So they are kind of my suppliers. So you can imagine it's like a consulting engineering company, and I go to this technology center and say, please develop this breaker for me. But then maintaining the team and having the line management and the right hirings and so on.
That's not your job anymore.
Not anymore. Yeah. I mean, I'm like to be involved. And of course, we discuss with the corresponding managers of the technology centers and the department heads and so on. But now, not anymore, really.
But because of your experience and sort of working your way up through that ladder, you really know it intimately, that whole process, it sounds like.
Yeah. So that's this thing, maybe why you called me like this full electrical guy. I mean, I really grew up in that from the research via different positions in the technology center. So I know the setups quite well. Right?
The ins and outs. What do you do specifically to make sure those products are safe at all those different stages that we've alluded to?
I mean, we work according processes, right? So we have like a certain new product introduction roadmap and process. And then during the whole design phase, we run reviews of design so that people document and check for risks, for safety. There is health and safety responsible for each project and product development. And at the end, as I said, it's very standardized. So you need to fulfill international standards, international law. So if we work, for instance, with pressure devices, so you have requirements. You cannot put a pressure device in the field if you do not kind of have a certification that it fulfills, 5 times the operating pressure.
So for ease, do you try to make sure that the products across the board cover all those different international standards? Or do you say this product is only going to customers in Germany, so we're only going to worry about standards that are applicable to that market?
That's a good question. I mean, we try to be as global as possible. So like the latest development, for instance, we certified for a very big standard is the international, the ISE standard, but there's also the American standard, the IEEE and so on. And there we certified from the beginning for both because the effort for certification is quite high.
Yeah, I would imagine.
And you try to cover with that almost everything. You say, okay, I covered the ISE and I covered the IEEE, so the international one, the American one. But there is still the Japanese standard. And then there is still, as you say, especially in Germany, some special customers, they say, but I want this on top, right? They have their customer specific requirements.
Right.
This is sometimes a bit difficult because you cannot kind of serve all of them at once, right? Yeah. So we try to really stick to the standards. But if there is, of course, big important customer, then there are dedicated tests for this customer. Some customers also come and they say, fine, you have this product, it's certified, but I want that to be repeated. Yeah. Right. I want to be present during this testing and witness this.
Oh, interesting.
So they then will run a campaign with them together sometimes.
That's fascinating. Do you ever get customers saying, oh, I saw that company in Germany has that and we're here in Canada and we want that too, but our government standards don't allow that? What do we do?
No, I mean, me personally not, but there are some special customer requirements. Especially the big customers, they sometimes have something like their own standard, right? They say they write a spec which is almost same thickness as the standard itself, and they say we want that. And there are other customers which do not care about certain things, right? Because they're saying that's not what we have in our grid. Yeah, typically it's okay to just follow the international ones. Yeah, I mean, that's complicated enough, right?
It's a lot to navigate, I'm sure. That. What about upgrades? How often are products tweaked or further inspected in the lifetime of a product?
I would say that's quite common, right? Because the industry is conservative, right? We talk about electricity grid. The things are out there for 20, 30, 40 years. So the customers are not some customers are not that eager to say, yeah, I want like every year a new product or something. Right, they say, okay, show it that it works for 10 years, then I might consider a new technology. So therefore, if let's say the current product is, let's say, not good enough for some reason, because also the electricity grid or the demand side changes, right? And there's more short circuit power needed and so on. And say, okay, we need the next generation. Then typically it is based on the previous product, and you know what it can do and where its limits. And if you hopefully understood why there are these limits, you can make the next generation more efficient, smaller, faster, better, and so on. So that's quite common, but we have now this big change from this one technology to the other. So it's a bit, I don't know, if you compare it with the car industry, when you have the move now to electric cars, we have the same a bit move from this one insulating gas, we have gas switchgear. So from this SF6 gas to the Eco product. But this is really a new technology. So we kind of do not invest further to develop the next tweak of the SF6 technology.
So you've mentioned Econic a few times briefly.
Yeah.
I feel like maybe now might be a good time to get into that more. Over the next few episodes of our podcast, we'll hear more about this innovation of Econic, which I understand is the eco-efficient achievement that Hitachi Energy is most proud of right now in high voltage. Can you tell us a bit about the process of bringing Econic to market and what that was like, how long it took? What were the sort of surprises and obstacles along the way in that journey?
Yes. The process itself started decades ago, right?
Yeah.
So the Econic,
before you were here, I assume.
Yeah, before I was here, exactly. Yeah. So when I joined 2006, the research center from ABB at that time, there was already research ongoing on eco-efficient solutions, because up till now, we are still using the certain insulation gas, SF6, which is great in all respect, in insulation and interruption, what we need for our switchgear. But it has just a very high global warming potential. Actually, it's the highest one you have for a substance.
And for those of us outside of the industry, how do you measure the carbon footprint, that classification that you just said about SF6?
Why is it so high?
Yeah.
Okay. One thing, I mean, I'm not a chemist, right? But
Sure.
I mean, I think I should manage to say that. It is a very stable molecule. So one thing is the lifetime, how long things survive in the atmosphere. And
Right.
SF6 that's why it's so great. It's so super stable that it survives 10,000 years or whatever is the number. Now somebody will say that was the wrong number, but very, very long.
But for better and for worse, it doesn't break down. Is that
exactly?
Yeah.
It doesn't break down. And the second ingredient to get a high GWP, so global warming potential, is that it has the absorption in a certain range of the spectrum, right? So you have light coming from the sun, which is mainly energy comes by UV, and infrared is typically going out. So if like in a car, right? If it gets hot inside, no, and so SF6 contributes to the screening of the radiation going out, right?
Right.
So you have a high GWP, but beside that, you have excellent properties. It's super stable. It has it gazes in the right range between in our operating temperatures and operating pressures. It has great insulation properties. It can withstand 3 times the withstand of air. If you want to withstand voltage, you can make things much more compact. That's the purpose of gas-insulated switchgear. And then if you put it in high pressure, even more, so you can make things very, very compact with that. It's like non-poisonous and so on. So it's very, very nice properties. It was used in the past a lot for various applications, but it was banned for a lot of things where you don't really need it, but it is still used in power industry.
I think people had it used in Nike shoes and in tennis balls, right?
Yeah, I heard the story as well, and then some window glasses. So in the windows, in the glass between
double glazed windows,
exactly, because it has this very good kind of big molecules, does not go out. It has good insulation and so on. So it was used in tires, I heard, but I don't know if that's all kind of
might
true.
all just be rumors. Yeah.
Yeah. I think it's true, but it's still used for certain special applications. And now regulations are upcoming to ban it even there. Therefore, this research on the alternatives, so for our eco solution, went on since decades. And then at some point we've reached a level where you can develop products out of that. And we have went out with a few products. And you start typically, I'd say, at the lower voltage. Okay, that's somehow easier to achieve. And now the big kind of milestone we have reached, and last year we have put a product out for this 420,000 volts, so 420 kV, which is the highest voltage level in Europe at least.
Again, for listeners who aren't in the industry, what kind of machinery, or how would we make an analogy in our heads for what uses that amount of energy?
Maybe it's not about energy, but you can consider the electric grid as like the road system, right? Yeah. You have highways, you have some, how do you call it, country roads, and then the small ones, right? Yeah. And the highways in Europe at least are at 420 kV. So 420,000 volts.
Those sort of grid highways.
Exactly, the grid highways. So the big ones, when they are typically next to the highway. So if you go by car, you see them, right? Yeah. And you need to basically switch on and off because it's a network, and you need to switch. There might be a lightning hitting. There might be, I don't know, something broken. If a tree falls on the lane or something. So you need circuit breakers to interrupt that. And you could say that if you go up in voltage, it becomes more difficult to switch that, right? At home, you have also circuit breakers, those which you have in your cabinet where, this small circuit breakers.
But sort of the more electricity that's running through those circuit breakers, the harder it is.
Exactly. So the more voltage, the harder it's to manage, and the more the short circuit power. So the more, if you create a short circuit on this highway, right? This is a lot of power behind which you need to interrupt and to stop.
Yeah.
When you develop a new technology, therefore it was started like from the bottom, from the country road somehow, right?
Yeah, right.
But last year we put out this 420 kV breaker, and this is the big kind of achievement and milestone also to demonstrate that the technology can cover everything, right? That you can phase out SF6 and cover all you need. And next ones are on the roadmap. 550 is now under development, actually, will be released soon, which is the highest voltage level in US. Maybe they have even 1,000. I don't know, 800 I think they have as well. But 550 is the longer the distance, the bigger is the voltage typically, right?
I see. Okay.
Because you want to minimize your losses. You want to put a lot of energy from A to B, and the higher you go up in voltage, the more you can transmit with kind of the same current or lower current, and then you have for long distance high voltages.
So presumably those higher voltage circuit breakers are going to be more of interest to larger countries with larger expanses to travel. Is that right?
Yes, for those above 420, because 420 is really this grid in Europe, and other countries, of course, have also 420. But for the big bigger countries like US or China, they have a lot of 550 or even 800, or some have even 1100 kV.
Right.
This we don't have here because it's not economical in a way.
Right.
Because you don't have such a big distance to bridge, right? And you need two transformers to go up and down in voltage and so on.
And so what's an example of one of the hurdles you've had in making Iconic work for those larger voltages?
Ooh, that's a good question. One hurdle I would say during the development phase is that before we were talking about this tweaking and upgrades, right? So if you start developing something new, then you realize what you are missing. Because if you say, I base it on this one and upgrade and say, but now on what do I base it, right? So you start this fundamental discussions. Should I use this technology or that? So we have single motion, double motion, self-blast, puffer breakers, a lot of different technologies. So first you need to agree among all these experts what is the best choice to start with. And
so is there a lot of sort of arguing and discussion around which way to go?
Up to even personal favorites, right? And then there is also, you need then all the tools, right? Because our tools, we use a lot of simulation tools, and those we have developed over the last decades and improved. And now suddenly you need to do all your simulations for a new gas. And those simulation tools, you need electric data, thermodynamic data, and this data first needs to be established, to be found and validated actually, because we don't want to do trial and error to be fast and efficient. You want to predict something really well. And if you want to do a flow simulation inside a gas circuit breaker, for instance, you need thermodynamic properties of the gas, let's say over temperatures from 1 to, more than 100 bars, and temperatures from 0 to 20,000 Kelvin, because we have temperatures like in the plasma, which is very, very high.
Right.
And this data needs first to be calculated or measured by that's decades of stuff. And then you need to put it in a simulation tool. And you say, but is it right? We don't have any comparison, right? Yeah, right. It's the first time developments are a bit exciting in a way, right?
Yeah, you're sort of out in outer space on your own without anything.
So the obstacles you were asking were like, we had also our mind on the known technology. And sometimes, but that does not behave like we are used to, right?
Yeah,
so then you had to adapt a tool or your model and then repeat it, and things work out. Now then you can use that, of course, to the next voltage level, next tweaking and upgrade, as you called that previously.
Is that an exciting process for you? Or I can imagine there's probably exciting elements and also times when you're just sort of scratching your head with frustration.
Yes. I mean, I find it in general very exciting because it's like developing new things. And if you look at the times, we invest a few months to develop a variant or a design, and you do all these discussions and challenging and simulations. And then you finally decide on a certain design, and then everybody's like waiting the test, right? Because at the end you need to prove it in the test. No, and then there is the like a
everyone's
chat
biting their nails.
Yeah, there is a chat ongoing on Teams, like, okay, now this shot is to come, and so on. And people, is it correct or not? Yeah. So that's quite exciting for me, at least. So it's fun to see that happening and people discussing and improving these things. It's quite cool, yeah.
Yeah. Why is this portfolio so important in your view?
I mean, the Iconic portfolio is important for us as a company, you could say, because if you don't have it, you're out, I would say. Also from the society point of view, right? We want to really go to reduce the carbon footprint, right, of the electricity grid. And this is only possible if you go and replace step by step the SF6 solutions. So it's in both terms somehow important. And now also, since it's coming, also the customers requested, they say, we are out of this kind of fancy prototype phase. Like again, like with the electrical cars, they were also around for 20 years, right? And just some kind of nerdy people had one, right? And now it's like becoming reality.
The demand is up.
Exactly. And then also the legislation is coming because they see, okay, there is a solution. So why should we allow the other solution be around when it's so environmentally harmful? That's why this is like, there is no way back, right? Yeah. Therefore, if we do not develop it for the company, I would say we would be out of business at some point.
Yeah, right. So that's why it's so important to the future of Hitachi Energy is basically responding to client demand. Is that right?
Yeah. Yes, client and you could say society demand somehow, right?
Yeah, social demand, exactly. This has been terrific speaking with you. Thanks for joining us today, Markus. You've given us a really terrific peek into the complex and crucial steps in research and development at high voltage. Thanks for tuning in to this episode of Power Pulse. Until next time.
And that's it for today. We'll be back soon with some more great content. But before you go, remember to give us a follow so you don't miss an episode. Thanks for tuning in. See you soon. This episode was brought to you by Hitachi Energy. Created and introduced by Barbara Freitas-Daniels. Content and script writing by Cassandra Inne. Guest speaker Markus Bujotzek. Hosted by Sam Dash. Produced and edited by Creative Chimps.